Actually, Euler proved that even perfect numbers are of the type 2 raised to p minus 1 into 2 raised to p minus 1, where p is a prime and mp is 2 raised to p minus 1. This is also a prime. mp is called as a Mersenne prime. Euclid had shown that numbers of this type are perfect numbers. This was in about 300 BC, whereas Euler showed that all even perfect numbers are of this type. Here the number mp, which is 2 raised to p minus 1, this may be prime or it may not be a prime. If it is a prime, it is called as a Mersenne prime. The name of Mersenne was given to these primes because Mersenne in 1644 announced that mp, this number 2 raised to p minus 1, is prime for the following values of p. P equal to 2, 3, 5, 7, 13, 17, 19, 31, 67, 127, 257. So he claimed that these are the values of p for which 2 raised to p minus 1 is also prime. Primes up to 257. He gave a list of such primes. Of course, at that time it was not easy to do calculations of large numbers, and in his list it was found later that these values 67 and 257, they are erroneous. So for these primes p, the number mp becomes a composite number. On the contrary, some values less than or equal to 257 were missed by Mersenne, and these are 61, 89, 107. These are the primes for which 2 raised to p minus 1 is also a prime. So these are corresponding Mersenne primes. If you get a Mersenne prime 2 raised to p minus 1, then multiplying it by 2 raised to p minus 1, we get a perfect number. And perfect number means a number for which the sum of its proper divisors is equal to the original number. An example is 6. 6 is a perfect number. 1 plus 2 plus 3, that is 6. 1, 2, 3 are proper divisors of 6, and their sum is also 6. This is a list of some initial Mersenne primes and corresponding perfect numbers. So mp is 2 raised to p minus 1. 2 raised to p minus 1 times mp, that's a perfect number. So 2 is the value of p. 2 raised to 2 minus 1, that is 3. And multiply 2 raised to p minus 1 by this number. So 2 raised to p minus 1 times mp, that is 6. Next, suppose p is equal to 3, then 2 raised to 3 minus 1 is 7, and 2 raised to 3 minus 1 is 4 multiplied by 7, that is 28. This is a perfect number. If you take p equal to 5, 2 raised to 5 minus 1 is 31. Multiply 31 by 16, that is 2 raised to 4. 2 raised to p minus 1, 2 raised to 4. So that is 496. That's a perfect number. If you take p equal to 7, then 2 raised to 6 multiplied by 2 raised to 7 minus 1. 2 raised to 7 minus 1 is 127 multiplied by 2 raised to 6, and that number is 8128. Likewise, take a prime p, like if you take 11, p equal to 11, then The corresponding number MP is not prime, it's a composite number. So it is not a Mersenne prime. We can call it as a Mersenne number. So if you take p equal to 13 and do this calculation, 2 raised to 12 multiplied by M13, then you get this large number. 17, 19 will also give you perfect numbers. They are very large. Although even perfect numbers are given by this formula of, you can say, Euclid and Euler. So for not many Mersenne primes and not many perfect numbers therefore would be found, because the value of MP becomes very large and it becomes very difficult to see whether this number is prime or composite. So far, only 47 Mersenne primes have been found. The largest one was found in August 2008. This was the 45th known Mersenne prime. And it is given by 2 raised to 43112609 minus 1. So this is a prime p equal to 43112609. 2 raised to p minus 1, that is also a prime that was checked by computer calculations. And once that is a prime, we have 2 raised to p minus 1 multiplied by 2 raised to p minus 1. That's a corresponding perfect number. So largest perfect number is given by this prime. This is also the largest known prime. Usually, if you want to find large primes, then Mersenne primes, that is the only solution so far, and largest Mersenne prime gives you largest prime. Now, here after August 2008, 2 more Mersenne primes were found. These are actually 46th and 47th Mersenne primes, but they were smaller than this number. This is the largest known Mersenne prime. And this number has 12978189, that many digits. Okay, so we shall now see the 2 raised to p minus 1 into 2 raised to p minus 1 for even perfect numbers. People have tried to find out odd perfect numbers, but so far they could not find any one. These perfect numbers were studied even by Pythagoras, and Pythagoras his time was approximately 569 BC to 475 BC. So Pythagoras and his followers, they studied perfect numbers. Euclid BC was probably the first one to make a statement about perfect numbers and show that these are perfect numbers. So if P is prime such that 2 raised to p minus 1 is also a prime, then 2 raised to p minus 1 multiplied by 2 raised to p minus 1 is a perfect number. That is, sum of its proper divisors is this number. So let us give a proof of this result. Proof so we know the sigma function, which is the sum of divisors of n. Sigma n is the sum of divisors of n. So n is perfect means n equal to the sum of its proper divisors. Proper divisors means divisors other than the number itself. If you include n in this sum of proper divisors, then you get the sum of all divisors, and that is sigma n. So n is perfect if and only if sigma of n equal to 2n. And then for this number 2 raised to p minus 1 into 2 raised to p minus 1, you have to show that sigma of this number is 2 times the number. So consider n of this type. Let n equal to 2 raised to p minus 1 into 2 raised to p minus 1, where p is prime and 2 raised to p minus 1 is also prime. 2 raised to p minus 1 is also prime. Find out sigma of n. It should be 2n. Let us see. Sigma of n equal to. Note that this is an odd number and this is the power of 2. So these two are relatively prime. And the function sigma n is a multiplicative function. Multiplicative function means that f of mn equal to ff into fn, provided mn and are co-prime. So here sigma n will be sigma of 2 raised to p minus 1 multiplied by sigma of 2 raised to p minus 1, since 2 raised to p minus 1 and 2 raised to p minus 1 are co-prime. And sigma function is a multiplicative function. This is, note that this is multiplicative. So what is sigma 2 raised to p minus 1? The divisors are 1, 2, 2 square, etc. up to 2 raised to p minus 1. And the sum of these divisors is 2 raised to p minus 1. So sigma of n equal to sigma 2 raised to p minus 1 is 2 raised to p minus 1. And what is sigma 2 raised to p minus 1? Note that 2 raised to p minus 1, this is assumed to be a prime number. The divisors of this are only 2, namely this number plus 1. And their sum of divisors of 2 raised to p minus 1 is 2 raised to p minus 1 plus 1. This 2 raised to p. So this is 2 raised to p minus 1 multiplied by 2 raised to p. and this you can write as 2 times the number n, because what is n? N is 2 raised to p minus 1 into 2 raised to p minus 1. Multiplying this by 2, you get 2 raised to p here and this. So sigma of n is 2n, and that means that n is a perfect number. This was the result of Euler. Euler stated it in a somewhat different way, that he said you go on finding powers of 2 and add them, like 1 n plus 2, this is 3. Once you get a prime, you multiply that prime by this last number, and that's a perfect number. So multiply the sum, that is 3, by 2, so this gives you 6. Similarly, 1 plus 2 plus 4, this is 7. This is a prime number. Multiply this 4 last number by the sum, that is 28. That's a perfect number. The next example is 1 plus 2 plus 4 plus 8 plus 16. This is 31. This is a prime number. Multiply that by 16. 16 into 31. So this is 496. This is a perfect number. So Euclid stated this result in this fashion. In the modern language we are writing it as, if p is a prime and 2 raised to p minus 1 is also a prime, then 2 raised to p minus 1 times 2 raised to p minus 1 is a perfect number. Now these perfect numbers are even perfect numbers. And people tried to find odd perfect numbers, but they were not successful in that. And so far no odd perfect number is known, and people have not been able to show that there is no odd perfect number. Also the question is, are there some other perfect numbers than the perfect numbers given by this formula? Euler was able to prove that these are the only even perfect numbers. So that's the theorem of Euler. So the result of Euler, that is converse of the result of Euclid, was obtained about 2000 years later. So that's the result of Euler. (1707 to 1783). Every even perfect number is the type (2 raised to p minus 1 into 2 raised to p minus 1), where p and 2 raised to p minus 1 are times. Let us do this result of Euler. Suppose n is an even perfect number. So if n is even perfect number, n is divisible by 2, so we can write n as power of 2. Now that power of 2, let me write for convenience as 2 raised to p minus 1 times m, where because n is even, I must assume p bigger equal to p in integer bigger equal to, and this m is an odd integer. M is an odd integer. So whatever power of 2 is present in n, we take it out and the remaining number we write as n. Also, because n is a perfect number, sigma of n must be 2 raised to, sigma of n is 2 times n, and that is 2 raised to p multiplied by n. Here we do not know at present whether p is prime or not, but we will show that p is a prime number. Not only that, we will show that m is also a prime number, and it is of the form 2 raised to p minus 1. Okay. Now m is odd, so what is sigma n? Again, recall that sigma is multiplicative. Now sigma is multiplicative, and these factors of n, namely 2 raised to p minus 1 and m, they are co-prime. Therefore, sigma of n equal to sigma of 2 raised to p minus 1 times sigma of m. That is, what is sigma of 2 raised to p minus 1? It is 2 raised to p minus 1 times sigma m. And here it is 2 raised to p times n. Sigma of n is 2n because n is, so we can write it as 2 raised to. This shows that this 2 raised to p minus 1 divides the left hand side, and 2 raised to p minus 1 is actually co-prime to, therefore 2 raised to p minus 1 must divide n. Now 2 raised to p minus 1 divides 2 raised to p into n. So 2 raised to p minus 1 divides n, because it is co-prime with 2 raised to p. So let us write m equal to 2 raised to p minus 1 times a number, let us say r. So write m equal to 2 raised to p minus 1 times r, where r is a proper divisor of n, where is a proper divisor of n. Because this is bigger than 1, p is bigger equal to, so this is bigger equal 1. In fact, bigger than 1. This is bigger than 1, so r is a proper divisor of n. So, if I take the sum m plus r, this is the sum of two divisors of n. What is this? This is 2 raised to p minus 1 times r plus r. Now this minus r and plus r gets cancelled, so it is 2 raised to p times r. Okay. So what is sigma of m? You can look at the previous result here, that 2 raised to p times m is 2 raised to p minus 1 times sigma m, where m is 2 raised to p minus 1 times r. So you can say sigma m multiplied by 2 raised to p minus 1, that is from the previous result 2 raised to p times m, and m is 2 raised to p minus 1 times r. So 2 raised to p minus 1 gets cancelled and sigma m is 2 raised to p times r. Therefore, sigma m equal to 2 raised to p times r, and that is equal to m plus r. We have calculated m plus r, and that has come out to be 2 raised to p times r. Now this is a very useful statement. Here sigma m is the sum of all divisors of m, whereas m plus r is the sum of just 2 divisors of m. Now m is itself there, and this r is a proper divisor of m. What about other divisors? Because sigma m equal to sum of these 2 divisors, it means that m does not have any other divisors, and therefore m has exactly 2 divisors. Exactly 2 divisors, namely m and r. What does that mean? This means that m has to be a prime number. M is prime, m is therefore r, which is a proper divisor of m, must be 1. So m is prime and r is equal to 1. We know that from the properties of divisor function, suppose n is e1 raised to a1, etc., e r raised to ar, then number of divisors is a1 plus 1, etc., ar plus 1. So each of these is at least 2, and if suppose any one of the AIs is bigger or equal to, then that factor is at least 3. Number of divisors is at least 3. If all of them are equal and the number n is not prime, then it would mean that this is the product of numbers which are at least 2. So 2 each, and then product will be in any case bigger than 2. So prime numbers are the only numbers which have exactly 2 divisors. Composite numbers with more than 2 divisors. So here m is prime and r is equal to 1. So what is the meaning of r equal to 1? So m is 2 raised to p minus 1 times r. R is 1, so this is 2 raised to p minus 1. Moreover, two raised to p minus 1 is prime. We can deduce that p itself is a prime number. The reason for this is the following. Suppose P is factorizable as P1 into P2. These are some integers. Then what is 2 raised to P minus 1? This is going to be 2 raised to P1 P2 minus 1, and then this can be written as 2 raised to P1 raised to P2, and then 2 raised to P1 minus 1 will be a factor, and you will get some other factor here which is bigger than 1. So this number 2 raised to P minus 1 will be a composite number provided P is composite. So that's what we have written here, that if this is prime, then P itself must be a prime number. So we have shown that thus if n is perfect and even, n equal to 2 raised to P minus 1 times n equal to 2 raised to P minus 1 is prime, P prime is also prime. That's what was to be proved. So because of this result, we get all the even perfect numbers. So we can say it is Euclid-Euler theorem that every even perfect number is of the form 2 raised to P minus 1 times 2 raised to P minus 1. These perfect numbers, they were interesting, and people use them for religious purposes also. They have some nice interesting properties. One of the properties is the following. Suppose I take 6 as a perfect number, and its divisors are 1, 2 and 3, and take also the divisor 6. Sum of all these divisors is 2 times 6, that is 12. Now let us look at the reciprocals and take their sum. What is this? You will see that the sum of these three is 1 and this is 1. This comes out to be 2. If you take some other perfect number like 28, this also has the same property. But take the reciprocals of all the divisors, including the number itself. So 4 plus 1 plus 1 half plus 1 by 4 plus 1 by 7 plus 1 by 14 plus 1 by 28. This also comes out to be equal to 2. And for even perfect numbers, we know how it looks like, so we can easily see that if n is an even perfect number, then summation 1 by d divides n is equal to 2. Okay, we shall now study some other arithmetic functions. One of the interesting functions is u of n equal to 1 for all n bigger than equal 1. This is an interesting function, and using this function we can write the previous formula like this. Formula for getting a new arithmetic function from old was discussed. So if f n is an arithmetic function, function capital Fn can be obtained from small f as summation fd d divides n. This can be written using the Dirichlet multiplication as f equal to small f star a function u, where this star is the Dirichlet multiplication. Let me recall that. So f g, they are arithmetic functions. Star g of n is equal to summation fd g n by d, sum is over divisors of. It is known that if f and g are multiplicative, then f star g is also multiplicative. And this function capital F, what is capital F? We can say that it can be obtained as small f star u, because what is f star u? And it is summation fd u n by d d divides. And what is u n by d? U is 1 for any value. So u of n by d is 1, so this is summation fd times 1 d divides. That is the function capital F of. So S star u is equal to capital F. And once you are able to write S star n, S star u like this, the property of Dirichlet multiplication, that if f and g are multiplicative, so is S star g. It is easy to deduce that capital F is also multiplicative if small f is multiplicative. So if g multiplicative implies if star g is multiplicative. This tells me that if f is multiplicative, since u is already multiplicative, because u of n equal to 1 for all n. So u is multiplicative. You get that their Dirichlet product, which is also called convolution product, f star u, is also multiplicative. That is, f star u is the function capital F, fn equal to summation fd d divides n is multiplicative. Now we will see some other functions. One interesting question is I of n, which is 1 if n equal to 1 and 0 if it is bigger than 1. This function works as identity for the Dirichlet multiplication. Let us see how. So find out f star I n. This is summation fd I n by d d divides n. Now, if d is a proper divisor of n, then n by d is bigger than 1, and then this I n by d is going to be 0. So only d equal to n will survive, and therefore it is f of n. For d dividing n, d less than n by d happens to be bigger than 1. So I of n by d is 0. So this is f of n. And h star I is equal to I star f. It is commutative property of star. That's equal to f. And that means I works as identity for the Dirichlet multiplication. Therefore, I works as identity for Dirichlet multiplication. Okay, we will now see the Mobius function, which is another interesting function. Mobius function. Here we are writing umlaut on O. You can also write it as, without umlaut we have to put additional e here, Mobius function. The Mobius function is defined as mu of n equal to 1 if n equal to 1. If n is product of distinct primes, say n equal to p1, p2, pr, then mu of n is defined as minus 1 raised to r. If n is product of distinct primes, p1, p2, pr. R distinct primes are there, then that R is taken here. And then we say 0 otherwise. That is, whenever n is divisible by a square, mu of n is 0. So, mu of n equal to 0. Suddenly, the square divides n or some prime p. Otherwise means n is not 1 and n is not a product of distinct primes. So at least one prime is repeating. In other words, we can say that n is divisible by some square bigger than 1. That is if and only is divisible by a square bigger than 1. For example, what is mu of 2? Mu of 2 is only one prime, so it is minus 1. Mu of 6 is a product of two distinct primes, so it is minus 1 raised to 2. This plus 1. What is mu of 8? 8 is divisible by a square, 2 square. So this is 0. What is mu of 100? This is a square itself, so this is 0. What is mu of 30? 30 is 2 into 3 into 5. There are 3 primes involved. This is a product of 3 distinct primes. So the value is minus 1. Now, this mu is also a multiplicative function. Un proposition even and summation ud d divides n equal to, if n equal to 1, 0, n bigger than 1, 0 otherwise. Multiplicative function means fmn equal to fm into fn if m and n are relatively prime. So here we look at mu of mn. So let mn equal to 1, CD of mn is 1. First consider, if mn equal to 1, these are positive integers, their product is 1, then m has to be 1 and n also has to be 1. So what is mn? It is 1, that is 1 into 1. This one is mu of m, because m is 1, and this one is mu of n, because n is 1. So mu mn equal to mu n into mu n, provided mn is equal to 1. Now consider mn is the product of distinct primes then so will be m and n individually. So will be and hence in m and n will be distinct. There is no prime divisor of m will be a divisor of n. Suppose m equal to p1, p2, pr, pi distinct primes, and n equal to q1, q2, qs distinct primes. So pi distinct primes, qj distinct primes, and no pi is equal to any qj. No pi is equal to qj, a qj. So pi and qj, they are different. Now what is mu of mn? Mn is a product of r plus s distinct primes. Therefore, this is minus 1 raised to r plus s, which can be written as minus 1 raised to r into minus 1 raised to s. And this is mu of m into mu of n. So in the second case also, we get the result. The third possibility that can be considered is that mn is not square free. This mn is divisible by some square of a prime. So suppose mn is not square free. So the square divides mn for some prime p. In this case, m and n are co-prime Therefore, p square divides either m or n, but not both. Suppose p square divides n. If we are using that, it doesn't happen that p divides m and one more p is dividing n. P square as a whole has to divide one of the numbers, say m. Then what do you get? P square divides m, therefore mu of n is 0. Also, mu of mn is 0 because mn is already divisible by p square. Therefore, mu of mn equal to mu n into mu n. Mu m into mu n. So we have three cases for mn, and in all these three cases the required property mu mn equal to mu m into mu n is satisfied, and therefore mu is multiplicative. Using this, we shall prove the second property, summation ud d divides n is 1 if n equal to 1 and 0 if n is bigger than 1. So, use that since mu is multiplicative, summation ud d divides n is also a multiplicative function. So, write n equal to summation ud d divides n. Since un is multiplicative, so is and therefore Fn can be obtained from values of capital F at prime powers. So write n equal to product pi raised to ai, I equal to 1 to r. This is canonical factorization. So this pi are distinct primes and ai are bigger or equal 1. Therefore, what is f of n? It is product of f of pi raised to ai, I equal to 1 to r. Now, these f pi raised to ai can be obtained as follows. F of pi raised to ai equal to mu of 1 plus mu of pi plus mu of pi square plus etc. plus mu of pi raised to ai. Here ai is bigger or equal 1. Therefore, at least these two terms are there. And if the other terms are there, like ai equal to 2, 3, etc., then these terms will be there. In that case, mu of pi square is 0, mu of pi cube is 0, and so on. So this part will not contribute anything. So this is mu of 1 plus mu of pi only, because the remaining part is 0. What is this? This is 1 and this is minus 1, that is 0. So f of pi raised to ai is 0. So whenever n is bigger than 1, you get factors like this for fn. Each of these f where f is 0 and f of n will be therefore 0 is bigger than 1. So thus for n bigger than 1, f of n is equal to 0. What is f1? Well, that is just mu1. Mention mu d divides 1, that is mu1, that is 1. Therefore, f of n equal to 1 if n equal to 1, 0 otherwise. And that is the value of summation mu d divides n. Up to the result. Now this Mobius function is useful in following result proposition. This is called as Mobius inversion formula. The proposition says the following: if capital Fn equal to summation f of n, f of d divides n. This is a function of n, d equal 1, capital Fn equal to summation f d divides n. Then you can get the function small f from capital F. And that is n equal to summation capital F of d mu by d. You can also write it as summation capital F of n by d mu of d, or you can write it as, this is all for d dividing n, d dividing n, d1 d2 equal to 1 equal to n f of d1 mu of d. You can get the original function small f from the function capital F by this procedure. शेवटचं बसलाय का? मित्र पुढच्या मध्ये घेऊ शकतो थोडं कष्ट होईल.